First of all, thanks to IIT Chennai, Professor Kamakoti, Madhu, and RISC-V Foundation for arranging this event over here. Secondly, I just wanted to ask some of you in the audience, how many of you are familiar with Western Digital? Okay, so that saves me a couple of slides on the company introduction. But one thing I like to highlight, Western Digital is definitely known for its storage products, but it is definitely not in the business of making microprocessors or selling microprocessors. So since last November, since Western Digital announced its weight or momentum or participation behind RISC-V, we are being asked this question that what is Western Digital doing in a CPU kind of consortium. So this presentation is mainly about our view of the world, which is coming from data and the storage side, and to highlight why exactly we are interested in RISC-V and why we are so committed to RISC-V. And then discuss and request all of you, to put your weight behind it, because any open source venture like this cannot be successful unless industry puts it weight behind it. And industry will go behind any such venture only if they say a business possibility. So we have to see it also from a business prospect perspective. The thoughts here are more from the data-centric world, not the data center world, but how the world is evolving into a data-driven economy. And then, we connect it to how RISC-V kind of open architectures are very suitable for us in this world of data-driven economy. So if you look back maybe 15, 20 years back, the role of data in the world, it was more used as a record. Whether your business is generating invoices or a bank is generating certain transactions, you are keeping all that, record in form of digital data. So it had a certain value that was limited for a period of time, but that's how the role of data, digital data started in the world. As the world evolved to, communication-driven economy, especially digital communication-driven economy, the role and value of data further evolved further. Today, whether we are doing the email-based communication or video communication or any communication of sort, it's all dependent on how effectively we are able to, move data across the world. And hence, the value of data is growing, and it's contributing more and more towards our economy. In today's world, data is being used to improve our efficiency. For one example is, in the past, people used printed maps, and now you have maps on your phones. It's nothing but a form of digital data, and the efficiency that it brings to the table is much higher than anything else we saw usefulness of data going forward. And not just the efficiency, but there are phrases you hear now in the industry that data is new money, even data is new oil, and that's not surprising because we are transacting our banking and money information through e-wallets, digital wallets, etc. And hence the role of data in our economy, day-to-day life is growing rapidly, and the value it is bringing to the table is growing more and more. Now, one of the thing that most corporates debate and struggle with, including our companies in the past, is more data more valuable or less data sometimes is more valuable? And it's a debate that I've seen many times in many companies. And it's a complex situation. Just to put things in a very simple perspective, you would see, I saw a very fascinating YouTube video of somebody known to me who have a dog who's able to identify numbers. So they write numbers from 1 to 9 in that video. They say dog 9, it goes and picks up 9. So a video of that dog is almost like 5 maybe gigabytes of data in high definition. But the online transaction I do on banking may be 100 bytes of data, but which is more valuable to me. And this video may be very valuable when you see it for the first time, but its value diminishes over time, whereas the value of other 100 bytes is more valuable to me. So just to simplify this world of how much is the value of large data, we at Western Digital has come out with a simple concept of simply dividing this concept into world of fast data versus world of big data. Now, the world of fast data is basically the data that is needed instantaneously at the edge device, like your smartphone or your car, or your IP video surveillance camera, or things like that. Any analytics that's going on at the edge, IoT devices and things like that. But you cannot afford to throw the large data. You have to, corporates are keeping the large data, banks have to keep by mandate data for a period of 7 years, telcos have to keep data, insurance industry has to keep the data. So there is a big value to the big data, and you have to store it very efficiently for a long period of time. But the way we have to handle that data versus the way we have to handle data at the edge is very, very different. And here comes the role of the processing, the kind of processing you need at the edge to handle the data instantaneously with very low latency, with very high performance, is very different from the way you handle data at the core or in a large data center where the size of data is very large. So that's where companies like us, which is custodian of roughly world's half of the data. So probably most of you do not know that Western Digital, at least in the hard drive industry, has close to 50% market share, and hence we proudly say that we are custodian of half of the world's data. And coupled with its acquisition of SanDisk, which brings a lot of flash storage capability to it, the storage and data becomes very critical to us. And then how do we handle that using the right processing elements is the angle that brings us to this kind of conference and consortium. Now, if you take example of, we are talking about connected cars going forward, or even autonomous cars going forward. It's not very far. Maybe next 3 to 5 years, we'll have such vehicles working. You cannot afford to have all the data at the back end on the cloud because of the network latency and the other issues. It may not have enough time to fetch the data and make a right decision instantaneously. So the processing that you need at that time, at the instantaneously on the edge, is very different from what you need at the back end. Now, the traditional CPU architectures that are prevailing in this world, they are very good. We have nothing against it. We all have used it. I worked for various processor companies before Western Digital. However, they are all designed for PC-centric world. They are all designed for general purpose applications. The good news in the past is because of the Moore's law, the semiconductor industry progressed so well that these general purpose CPUs kept on evolving and doing majority of the tasks very efficiently. Of course, we had very specific and unique requirements of processing in the past as well, for which the industry developed things like FPGAs, things like ASIC, or things like DSPs, right? The CPUs, general purpose CPU, could not do all the computing tasks. But now this is becoming more and more challenging going forward as the data is becoming more and more enormous, and the requirement of the fast data on the edge and the requirement for big data and the backend on the data center is becoming more demanding. And hence, in many applications going forward, the general purpose CPU may not be that suitable, especially when it is coming with predefined restrictions or predefined parameters. This is an example of a general purpose, commercial off-the-shelf CPU card. These are available from various companies, as you know, Arduino, Raspberry Pi, and so on and so forth. This is very good for general purpose applications. However, these have certain limitations in the sense that there are predetermined ratios already defined by the processor vendor or the board vendor in terms of what operating systems can be used, what type of applications you can run, and how much DRAM you can use, and how much memory for storage you can hang on the CPU bus. All this is well defined, and there's not too much scope for innovation, for us in the industry in many of these cases. So this is essentially a CPU-centric architecture, and here in a data center-centric world, we need something that is more data-centric architecture that allows us to innovate in terms of what kind of IPs we can connect outside to the CPU. And this is the reason why Western Digital, after using variety of standard processors for its own products, decided to join the RISC-V consortium. Last November, we made the big announcement, and we just started the work a couple of months before that. So it's not even 1 year since we joined this consortium, but we are already having a big momentum in the company, and many of my colleagues from our ASIC and SoC group are here in this conference who are actually presenting various papers. This is just a sample of the first product that we are developing for own use. Again, just want to highlight that we are not in the business of selling CPUs or processors in the market. We are doing all this to be used in our own storage products, basically. So the first implementation that we are doing is with the RV32 IMC core. And obviously, you know, this is more at the low to mid end of the spectrum of the performance. It's not a super high-end core. And this is two-way superscalar, mostly in-order core with 9-stage pipeline. And in terms of the performance, it's a low to mid-tier performance. And of course, our innovation is more on what we put outside the core rather than in the core. Core comes obviously from the RISC-V foundation. So how we are using this particular core and what application we are using today. So you know, as a company, we make millions and millions of products, both the hard disk drives and the flash SSDs. So first SoC implementation of this RISC-V is being done as a controller for NAND flash control inside a consumer-grade SSD or solid-state device. SSDs are used now very, very commonly in our laptops, desktops, and MacBooks, all these applications. And in this implementation, we have main CPU, data path CPU, and the main work that our team is doing actually on the uncore or the outside core part. So when you have the NAND flash memory management, then I think there's a lot of work that goes on in the error correction algorithms. And also the NAND controller part is our own proprietary intellectual property. And on the host side, this SSDs may have variety of interfaces. It could connect over SATA interface, SAS interface, or now the new industry interface is PCI-based NVMe protocol. So this is the first implementation that's going on in the company, and this will be taping out in a couple of months from now. And I'm sure my colleagues in some of the paper presentations will talk more details about it. Now with RISC-V, as a company, what we are finding is the flexibility it's giving us and not the restrictions on the buses, you know, that are coming out of the CPU. So it's, you know, allows us to innovate, create our own, you know, IPs and connect them to this core, both on the client or consumer side applications, which are more embedded applications. We make flash memory for embedded applications in the form of eMMC or UFS flash that connects to the standard CPUs for the smartphone application, for SSD applications. But again, inside the eMMC, we need powerful controllers to manage the NAND and take care of error corrections. So both at the embedded application, RISC-V implementations are very, very suitable to us. And also, we do a lot of work on the enterprise and data center storage side, where the amount of data we handle is much, much bigger. And there, RISC-V gives us, you know, ability to, again, innovate on the how much memory you can connect to the CPU here. You could have RISC-V implementation. You could also connect them to FPGAs. Now we are seeing the variety of, in fact, one of the leading processor company buying a leading FPGA company. And that shows how specialized processing is the need of the hour, even in the data center or the server world, right? So RISC-V we find suitable both for embedded and enterprise applications similarly. Just to simplify, what we are talking here is most of the world uses, let's say, a general purpose transportation to commute from point A to point B. It could be a car, four-wheel car with 4 doors there, but not for every transportation requirement a standard car is suitable. For if you have to carry very large number of people, you might require very large transportation. That's a unique need, right? That's like big data environment in a data center environment. Same way, if you are commuting at much rapid pace, then you require specialized transportation there. That's an analogy for inventing the right CPU for the right application or right use case there. So RISC-V allows us this workload diversity, you know, which demand different technologies and different architectures. In the fast data world, for example, the architectures are more memory-centric because you have to cut down on the latencies. And hence, there is implementation using, you know, these CPUs could be in the form of ASIC or GPUs. GPUs are now very, very commonly used in variety of applications, more than graphics, for which they were invented. Now they're being used in machine learning or artificial intelligence. And on the big data world, which is more storage-centric architecture, where we need very large capacity hard disk drive. For example, today we are shipping 14 terabyte of hard drive for data center, and SSD in 8 terabyte capacity. So for the storage-centric architecture, again, we find RISC-V implementation very suitable because it allows us to make the required modifications that we need to do, large amount of memory to be connected to this. So hence, in a data-centric environment, which is divided into the world of the processing at the edge and processing at the big data side, you need very open architecture that allows us to innovate and develop products for the industry as we like. So on the big data side, there is a lot of analytics work that is going on in the industry, as we all know. Machine learning is going on, which requires, again, massive amount of storage. And hence, companies like us are developing storage at very, very massive scale and requiring CPUs that can handle that capability. Similarly, on the fast data side, the analytics at the edge, there is activities like event correlation or blockchain technologies or security-related stuff that is going on that require, again, large memory and specialty processing, again, for which we find RISC-V as an architecture very open and very suitable to these applications. Now, coming to the questions that some people ask, even in our company when we are debating on the RISC-V or any other open source architecture, there are debates about the ecosystem, the support, et cetera, et cetera. But if you look at some of the other open source initiatives in the world that have happened in the last 20, 25 years, some of them have been very, very popular. Today, all of us are connected to many of these things which are on this slide. However, it takes a long period of time for the momentum around the ecosystem, open source ecosystem, to build up. Linux was started in 1992, but not much momentum was built behind it until, I think, 99, when IBM decided to put its weight behind Linux momentum and invest significant amount of money into it. So similarly, an initiative like RISC-V will take a time. It will evolve over a period of time. And companies like us are putting its weight behind it, and I'm sure many other companies will come forward to put their commitment behind it. But if you see many other things on this chart, Ceph initiated maybe 15, 20 years back on a very small scale. Ceph is basically a storage file system which is distributed, scalable, and today most of the large companies in the e-commerce space or the cloud service space are using open source Ceph as their storage file system. TensorFlow is, from the Google for the analytics and the algorithmic search processing capability, and Hadoop is for analytics. So number of open source initiatives have become extremely popular and extremely useful to the industry. And same way, we believe with all of us in the industry and academia coming together behind RISC-V, this could be very, very successful going forward in the future. Now, at the edge, particularly, we are looking at things like security is becoming a big concern around the world. And even in India, now we see with smart city projects, video surveillance cameras being put around the world. So in the past, all the cameras were capturing the video and just dumping the data at the back end. So whatever analytics you could do was more after the incidents have happened. But now if you're able to put low cost, highly capable CPUs and the analytics capability on the edge in the camera, it could do a lot of predictive analytics. And similarly, variety of edge applications could get highly accelerated using the RISC-V innovations. So the advantages of RISC-V we see as a company, it's open and free. So obviously it allows us to innovate. Today, some of the great and very successful CPU architectures in the industry, we use them as well. Nothing against them, but they're putting a lot of restrictions on the, on the buses, et cetera, and hence limiting the innovations that companies can do around these. Also, the another advantage is RISC-V allows you to implement very low-cost, low-end implementations starting at 16-bit up to very high-end implementations. So one architecture, maybe common tool chain, common debugging, et cetera, allows you to build products which are very, very wide range in the industry. Also, it scales from the embedded applications all the way up to the enterprise application. and for the special purpose applications, allow you to write your own instructions as well. So in summary, very, very suitable for fast data. For example, autonomous machines like autonomous cars going forward, safety, security, like analytics in the IP video surveillance world, and similarly very, very suitable for the big data world doing predictive analytics or genetic research, genomic research, machine learning type of application. The good news is we are happy to see it's not just us, that variety of other companies have made open announcements supporting RISC-V ecosystem, which is extremely important. And some of these are well-known processor companies. And also there are companies in the memory or storage world, and there are a variety of companies including companies in the internet world. Now this is extremely important, and this is not only important from the industry to come forward, but academic institutes to teach these kind of architectures and rally behind it, do research work in that. And this will also give rise to many startups that are able to do either IP development or tools development around this ecosystem. So I think it's already looking very good. The momentum is looking pretty good there. How we at Western Digital, what we can do, what we are doing behind, as I said, we are not in the business of making processors or selling processors, but we ship approximately 1 billion CPU cores as part of our own products in a year. Now, USB, SanDisk branded USBs are part of Western Digital portfolio. Micro SD cards, you may not be even aware, but all of them use a 16 or 32-bit microcontroller inside for the NAND flash management and error correction. Now, RISC-V implementations can be used there, and we start shipping large volumes going forward. This momentum will take several years because overnight we cannot change all the processors that we are using. But as a company, we have made announcement, we are standing behind it, we are committing to this RISC-V architecture and working towards developing new processor for our own applications there. In summary, we are contributing to RISC-V by supporting the development of open source IP building blocks for the community, actively partnering and investing in the ecosystem, and then openly, of course, coming and talking in these conferences and giving a message that we stand behind RISC-V ecosystem. So that's about my talk. In summary, let's together work towards such an open architecture and innovate for the data-centric world. As we have seen, this is very, very suitable both for embedded and high-end applications. Thank you very much for your time.
Yeah, Vivek, thank you for that nice talk. Just a quick question. I don't know if you're allowed to answer it from your company, but the 28 nanometer, some of my students at Western, they're taping out 16 and 10. Right. So I'm not sure where the 28, is it a free code you're giving to us, or is it a, where does the 28 fit in this new world? Huh?
That's the first implementation that we are doing in the company. But of course, if you look at our other implementations of the NAND flash, they have been at 15 nanometer in the past, 3 years back. And the nanometer-wise on the memory side, semiconductor NAND flash side, we have now moved to 3D NAND. And we are vertically stacking these dies, 15 nanometer dies, all the way up to 64 layer, and we are shipping. So it's not about technology, but the SOC team chose to do first implementation on 28 nanometer for all the reasons that I, of course, cannot discuss here, but we can talk offline. But it doesn't mean that going forward we'll not have smaller implementations.
So computation in memory seems to be a thing of the few years from now. So will computation in storage also be something that's possible?
Yes, it is possible. In fact, the industry, not just us, but the whole industry has been looking at storage class memory as well. So today, we are challenged with DRAM on other side, one side, and flash or hard drive as a storage device on the other side. Industry for a long time, at least the storage industry has been looking at if they can develop a DRAM-like non-volatile memory. But as of now, there's no commercial implementation available, but industry is working in that direction as well.